Feel free to put questions in the chat. My topic is opposite arrows. My first paper is Entropy in Time by Amge Gauker from Cornell and Clerk from U Chicago. My second is Opposite Thermodynamic Arrows of Time by Schoolman from Clarkson. I'll be using PhET simulations in my talk. To start off, we're going to watch a couple of videos. While watching, I'd like you to put in the chat whether you think time is moving forwards or backwards. So in the chat, forwards or backwards? Not too bad, right? Again, in the chat, forwards or backwards? One last round, forwards or backwards in the chat. If we define a direction of time based on entropy increase, we're implicitly making the assumption that the low entropy state was externally put there by a boundary condition. And it wasn't a rare fluctuation where all the particles happen to bounce off the same location. For macroscopic physical systems, the probability of such a fluctuation goes to 0. So we could actually define a direction of time based on entropy increase. Now you might ask, how do we prescribe a final condition for a particle? Well, it's not too different from physics 50. We can set the initial conditions by the launch angle, or the final conditions by specifying the landing location. In the paper that I read, Schoolman simulates two systems, one starting with an initial condition, another ending with a final condition. He couples the two systems by applying some interaction forces between all the particles. And here are the results of the simulation. For zero coupling, we see that system A, the circles, starts at low entropy, our initial condition. System B, the stars, ends at low entropy, our final condition. If we apply some coupling, then both systems spend more time at equilibrium, high entropy state. More coupling, more time spent at equilibrium. Then Schoolman introduces a perturbation at t equals 4, giving the particles a little kick. For zero coupling, the solid curves are the unperturbed solutions, exactly the same as before. The dash curves are the perturbed solutions. To better see the effect of our perturbation, Schoolman plots the difference between the two curves. And as we can see, system A, the solid curve, the effect of the perturbation happens at t equals 4. However, for system B, it happens at t equals 3. Now, you might be wondering, what about cause and effect? Well, hold on to that thought for a moment. If we introduce some coupling, the effect is minimized. Going back to physics 50, if we introduce some perturbation and if we keep the launch angle, then surely the trajectory after the perturbation is going to change. However, if we want to keep the landing location, then we're going to have to change the launch angle. And hence the trajectory before the perturbation changes. So as we can see, the phenomenon turns out to be not as mysterious as it seems. To close off, I made a little skit to keep you pondering. And with that, I look forward to your questions.